Thanks everybody for coming. I appreciate you being here. We're going to start talking about the second law today. So it's a bit of a departure from sort of the open first law stuff that we've been doing. But before we get to that, I just wanted to, I will have office hours also today at 2. But if someone has any questions, I know we haven't had a chance to really sit down very much since the exam. So if anybody has questions about the examination, I'm happy to entertain them now.
I did actually have a question about one of the questions in the multiple choice section.
Yeah.
I believe it was the last question, at least for me. I don't know if they're randomized for everybody, but let me see if I can find it real quick. I think I wrote it down. It was dealing with which of the two properties can always be used to fix a state. And I was wondering what the answer was to that one.
It's tricky because I think that sometimes people think temperature and pressure is the right answer, but it's not, right? Because temperature and pressure you can't use if you're under the vapor dome, right? So the trick in that one is that it's always. So if you read me back the answers, like if there's one that's like temperature and specific volume or specific volume and specific enthalpy.
I believe there was one like that, yeah.
Yeah, so they need to be two independent intensive properties. And so I think 3 of the answers, one of them was always extensive, like maybe volume or mass or something. And then I think that 2 of the answers, one of them said temperature and pressure, which is true most of the time you can fix a state there, but not all the time, because if you're under the vapor dome, temperature and pressure become dependent.
Okay.
Yeah, so that's one of those. I would imagine that that's a common error. We often ask a question that's kind of like that, and certainly historically, that's one people miss sometimes. And in part, I know when I was writing tests, a lot of times when I made mistakes, that I was going too fast, and maybe missed some of the nuance of a problem.
Okay, thank you.
No problem. Any other questions? So, Dan, can you see the correct answers? Because maybe I just haven't set it up correctly.
Yes, no, I sent you the email last week, I believe, and I can see them now.
Okay, that's good. And
well, actually, I couldn't see the correct answers, but I could see the answers that I put in.
So that's another thing I can go through. My courses, the defaults are always not good. So I'll try to make it so that you can see the correct answer as well, because I'm not holding those back, for a reason. So
do you think you could do that for the quizzes as well?
Yes, so I can go through and do that for the quizzes as well.
Okay, all right, thank you.
Thanks. I think it's just a series of radio buttons, and I gotta run the gamut and pick the right ones.
Okay.
Thanks.
I don't know if we have time right now because it's kind of long, but I was wondering, sorry if we could go over problem 2 at some point. That was the first of the long answer ones.
So I would definitely not mind going over how to solve the problem with you, but I would prefer to do it in office hours if you're available.
Yeah, that's what I was thinking. Is office hours is probably better considering how long the question is.
And I think that so if you'd like to talk about methods for how to solve particular problems, I'm happy to do that in office hours today too.
Okay.
Cool. Thanks. So, just because we're coming back, it's been a little while, right? It's important to remember, right, that what we've been focusing on is how to deal with these open system problems, right? So open system processes, right? And we're, I've sort of said that these are a little bit like Lego blocks, right? And then what we'll be doing, for more or less the third part of the class, right? Sort of a little bit on the second exam, and certainly from the second exam to the final, is we'll be taking these processes, whether they're open systems or closed systems, and putting them together to understand how how more complicated machines work, right? So things like aircraft engines or internal combustion engines or nuclear power plants or air conditioners, right? But before we do that, we have to really understand how to deal with systems, right? Or individual processes, right? And we've been talking about open system processes, right? And in just a very 10,000 foot view, for an open system process, we need to know where are we drawing the control volume, what's our system, what happens to the mass, right? Because with open systems, mass can come in and out, and we know that mass carries energy with it. So we need to know what happens to the mass before we can find out what happens to the energy. And for most cases, if you're analyzing an existing system, these are the only three questions that you need to answer, right? So this is, you know that the system is possible, right? Maybe you're working in a coal power plant and your boss asks you to check out what the efficiency of the turbines are today, right? You can do this. You know that the turbines are running, so you don't have to answer the question, is this thing possible, right? Maybe you've heard of the idea of a perpetual motion machine, right? So if I thought of a perpetual motion machine, it'd be like if I was biking into work, right? 2 pedals on my bike, and then I just let the bike go, right? There's no power source, no anything, but I put some energy in and it just goes forever, right? Now, obviously that doesn't work in the real world just because of how the universe works, right? So sometimes we have to ask ourselves, is the process possible? Now, this is a timely example because I just got back from camping. And one of the things we do when we're camping is we make a campfire, right? So, you set it up in, you get these logs, right? And, something to light them, right? So I could say my control volume is these logs and the air around the logs, right? Now, I start my fire, right? So now I'm burning, right? And what happens is there's some mass that leaves my control volume, right? Because there's smoke that goes up, right? And there's heat that comes out of my control volume too. That's sort of the whole point of making a fire, right? So you can do something like roast marshmallows or at least stay warm, right? It was funny because this was exactly what happens when you go camping in New York State. The first day was like 90 and super humid. Then we got this huge rainstorm, and then it was like 65. And then, it got back to about 80s and something by the end. So we got all 4 seasons. Well, didn't get winter, but we got 3 of the 4 seasons while we were there. So that was nice, right? But this is an open system, right? I could do a first law analysis on this, right? But here's what I can't do, right? So let's say I set up this campfire in such a way that I could capture all the mass that left with smoke. And then I could put back all the amount of heat that I lost. You'd look at me pretty funny if I told you that that meant that I'd have logs again, right? Even though I could set this up so that it follows, that it satisfies the first law and the second law, right? But I can't get back to the beginning, right? Another way that I like to talk about this is, again, maybe it's campfire related, right? But you can't take a match, strike it, let it burn, and then unstrike it and get a matchstick back, right? Even though you could set it up so that you followed both the first law and conservation of mass in those 2 different examples, right? So what this means is that the universe has a direction for individual processes, right? There's a sort of a direction that things go. You have to conserve mass. You have to conserve energy, but those 2 things by themselves are not enough, right? So that's why we need another rule, another law in thermodynamics, right? So even because otherwise, if all we had to do was satisfy the first law, right, then I could get my logs back, right? And I can't do that. So if you're designing something, right? So, this is pretty cool, right? So maybe you go work for Elon Musk when you're done, right? And you're doing something that's never been done before, right? So you'll need to draw a control volume. You'll need to figure out what happens to the mass, right? Even if it's a closed system, it's just what happens to the mass is nothing, right? And then you'll need to figure out what happens to the energy. But if you're trying to do something that's never been done, right? Or if you're trying to maybe evaluate some proposal that somebody gives you, right? But it's not like a working prototype, right? Then you might want to ask yourself, is this process even possible, right? Or is this thing that sounds too good to be true really just a perpetual motion machine, right? Which we know can't exist. right? So sometimes we'll have to do what we call a second law analysis, right? So the second law will tell us, so we need to satisfy conservation of mass, right? We need to conserve energy. And the second law tells us what's the natural direction of a process, right? So that's what this lecture is about. It's kind of an introduction to this idea of the second law of thermodynamics, why we can't have a perpetual motion machine, or maybe why you can't always get what you want, right? So in order to do this, the second law, right? So the first law, well, I guess conservation of mass is about things like mass, right? Or maybe specific volume, right? Times the volume. The first law in closed systems was about this property that we learned about called specific internal energy, right? Because it was, after we made some assumptions, it was delta U is equal to Q minus W. And then when we moved to open systems, we started to talk about specific enthalpy, that lowercase h, right? But there's another column in all of these tables that's lowercase s, right? Or specific entropy, right? And that's there so that we can do a second law analysis. So for the second law is about entropy, right? And entropy this is kind of like, thermal's tough because there's all these new concepts. And I think one of the most difficult concepts in thermodynamics is this idea of entropy, right? And you can read all kinds of descriptions. This is one that I like. In any natural process, there exists an inherent tendency towards the dissipation of useful energy, right? Now, we've been talking about the universe as a series of kind of energy transactions, right? Maybe we're giving up enthalpy in order to get work, right? But it's not exactly a free market, maybe, right? We can think about the universe as kind of being in between all these transactions, kind of taking a cut, right? Right? You learned about this in sort of a, maybe a high school physics class or undergraduate physics, right? This idea of friction, right? So even though you started with, you got yourself on a swing, right? And you let go, and you're changing potential energy into kinetic energy, but you actually don't get all of that potential energy into kinetic energy because you have some losses, right? There's some frictional losses or something, right? So there's this dissipation of useful energy. You can't keep all the energy in the system because there's always these effects, right? Some people talk about entropy as being some measure of disorder or randomness. Sometimes people will talk about, I don't particularly like this analogy, right? But people talk about, your desk or your room. If you don't do anything to actively clean it up, right, it's constantly getting more and more messy. Especially, I've strategically aimed the camera here not at my desk because my desk is always very messy, right? It's it's funny. I think maybe when I was in high school, there was somebody on their desk. It said something like, if a cluttered desk is a sign of an empty mind, or is a cluttered mind, then an empty desk. What does an empty desk mean, right? So it's my desk is never empty, right? It's always full of junk, right? So, but some people talk about that, but I prefer this idea of kind of striking and unstriking a match, right? Because I think it's really entropy is trying to tell us the natural direction of a process. I talked about a little bit earlier, I think that when I was in university, I read, what's it called? Stephen Hawking's A Brief History of Time, and didn't understand a lot of it. But one of the things that it talks about is that time is a little bit like this too. So time has this natural direction, right? Time only ever increases. Right? And we'll see what the second law is telling us is that entropy, all of the entropy in the universe also only increases. There's only one direction that this entropy is going, right? Somehow entropy is telling us about the losses in a system, right? It's, if you could make some kind of frictionless machine, then you would get rid of this idea of losses, right? And that would mean that you would not be increasing the entropy in the universe, right? But that doesn't happen, right? And I suppose I suppose we don't exactly know that it can't happen, right? The second law is kind of like, this experimental law, right? We don't know for sure that it's true, but we do know that every process we've ever looked at as humans, right, has losses in it, right? So we're pretty sure that this is true, right? That these losses are always in the system. Now, entropy, the second law, is a little bit different than the other sort of main equations that we're using, right? So we have continuity, right, which is conservation of energy, right? Or which is conservation of mass, I'm sorry, right? So that mass is always conserved. There's always mass. The other question is, we've got the first law, right? The first law of thermodynamics tells us that energy is conserved, can't be created or destroyed, right? But now we've got this new thing called entropy, and the second law is not an equation of conservation, right? And it's going to be this idea that it's not conserved that really helps us use the second law, right? So entropy is a little bit different than energy, right? But it's still kind of kilojoules, right? But it's this weird thing, kilojoules per degree Kelvin, right? That's the extensive version of entropy, capital S. But then little s, if you look up lowercase s in the textbook, it will be kilojoules per kilogram Kelvin. Just like all the other, or most of the other extensive properties we look at, we divide by the mass to make it an intensive property, right? So if this was imperial units, this would be something like BTU per pound mass degree Rankine, right? So it's energy per unit mass, but then we also have this temperature on the bottom as well. So what is the second law? We know it's got something to do with entropy, right? So the second law of thermodynamics tells us that the total entropy in the universe can never decrease, right? And the key word here is the universe, right? Because I can talk about particular processes where entropy is decreasing, like condensation. But if I look at the whole universe, the entropy in the universe is always increasing. Just like time, it's always getting bigger, right? Or that every system has losses, so we can't have perpetual motion, right? So if the entropy in the universe could, well, we can never decrease entropy, but it's not even that. We can't even break even, right? We can't get to a point where we do something and entropy even stays the same, right? Entropy is always increasing, right? If we broaden our lens enough to look at the whole universe, right? So the entropy in the universe is always increasing, right? And that means that we can't have a perpetual motion machine. So I got to keep pedaling on my bike if I want to keep going, right? Because there's always friction in the bearings there, right? And that's causing the bike to lose speed, right? Now friction is not a bad thing, right? Because if there was no friction, the good news is my bike wheels would keep spinning, right? But the bad news is I wouldn't go anywhere, right? Because the tires wouldn't grip the road or the dirt or whatever else I'm riding on, right? So it's not like friction's good or bad. It just is, right? And we certainly leverage the fact that friction exists for a lot of different applications, right? So friction is not the enemy here, even though sometimes it feels like it because it's robbing us of efficiency in all these different processes, right? So in any natural process, there exists this tendency towards dissipation of useful energy, right? So there's always losses, right? If I take a pendulum, right, and I let it go, it keeps swinging, right? But it dissipates, right? That's why if you've ever seen a grandfather clock, right, they've got the weights in there, right? And the reason they have the weights, right, you have to raise the weights every once in a while, right? And that's because the potential energy stored in those weights helps keep the amplitude of that pendulum the same, right? But what happens is as those weights fall, eventually some human has to come by, right, and lift those weights up. So you have to put more energy into the system because you're losing energy in the swinging of the pendulum, right? right? So here, right? So every process we call irreversible, right? So this is there's going to be a lot of definitions here. So an irreversible process is like that pendulum, right? Because as I let that pendulum go, it swings, right? And if I was doing first year physics, right, or high school physics, right, I'd let that pendulum go, and I'd say, oh, at the bottom, then it's all kinetic energy, and then it gets back to potential energy, and then back to kinetic energy, and now it would come right back up to the same place that I dropped it from, right? Because I wouldn't probably be accounting for friction in my calculations, right? But in real life, when I let that pendulum go, every time it comes back to me, it comes back a little lower, right? A little lower, unless it's in a grandfather clock, right? So that's the irreversibility of the process. It keeps going, right? But it's dissipating energy, right? So irreversibilities, right? So a process is irreversible because it's losing energy, right? So then something in the system that's causing an irreversibility is some way that the energy in the system is dissipated, right? So we've talked about, the big one for mechanical engineers is friction, right? So even in like the best bearings that you can get, as your wheel is spinning, you're losing energy, right? It's not a perpetual motion machine. It won't spin forever, right? When we were kids, we used to have, rollerblades, and we'd just sit there and spin the wheels and just watch them spin, right? But eventually you have to keep, hitting them so that they keep spinning, right? Because there's friction in the bearings, right? Another one that you may or may not know of, right? Well, obviously you know about it, right? Is that there's electrical resistance, right? So, those electrons, they don't pass through a wire for free, right? There's friction involved in that. Even these electrons, right? And you can make you can get a thicker wire to reduce your resistance, right? But you're still going to have resistance, right? And what that means, another way that happens here, just like friction, right? Like, I don't know if you watched the original Karate Kid, right? But Mr. Miyagi, right? He, puts his hands together and his hands get hot, right? Because of friction, right? Friction creates heat. Electrical resistance creates heat as well, right? I squared R, right? And we've used that a lot as humans, right? So, from your toaster to, I guess, incandescent bulbs are, hopefully becoming a thing of the past, right? But incandescent bulbs, it's resistance that's creating that heat, and it's that heat that's making that filament burn or glow very brightly, right? So electrical resistance, again, it's kind of a bad thing, right? If you think about it as, in the thermodynamic sense that it's a loss, but sometimes you can turn a loss into the benefit, right? Although, like we've seen, right? So it's not very efficient to be using, those old style light bulbs, right? In chemical reactions, there are irreversibilities, right? As different chemical bonds break, right? Or that, new chemical bonds are formed, then there's irreversibilities in those processes as well, right? So that's why, to get some chemical reactions going, you have to input some energy, right? In order for, to kind of get the ball rolling, right? So that's, there's irreversibilities in chemical processes as well, because there's irreversibilities in everything, right? Every single process that we do is going to have some dissipation of useful energy. And those things that are causing the dissipation of useful energy are called irreversibility. Okay, so if every process is irreversible, right? Like this pendulum, it doesn't come back up. Then what's a reversible process? Well, a reversible process would be if I let the pendulum go and it came right back up to the top, right? So the thing we need to know about reversible processes is that they don't exist, right? There's no such thing as a reversible process. But that doesn't mean, just because something doesn't exist, doesn't mean that it's not useful, right? So oftentimes, for us as engineers, it makes sense to talk about an ideal process, right? Or a reversible process, a process without any friction, right? Because this is like the limit of what's possible. We can't actually get to a case where we're, where that pendulum comes all the way back up, right? But we can get close, right? If we keep making better and better bearings, right, then we'll get closer and closer to this frictionless state, right? We can never quite get there, but that doesn't mean we shouldn't try, right? And that's part of the job of the engineer, is try to figure out where your irreversibilities are coming from, and maybe what's the low-hanging fruit, right? What's the problem that's where you can make an impact, right? Because if you could save, like if you could increase the efficiency of jet planes, right, by 1%, then I mean that's a phenomenal savings in cost, but also in sort of environmental emissions, right? So it's a huge deal, right? Even though it doesn't sound like a lot, oftentimes we think of 1% as not being a big deal, right? But same thing with a power plant. If you can improve efficiency by 1%, that's pretty great, right? So reversible processes don't really exist, right? They're like the tooth fairy that I'm showing in the background here, right? This is why I'm doing this lecture here from my office, right? Not at home where the girls are listening, right? Because these things don't exist. But just because they don't exist doesn't mean they're not useful, right? Sometimes we model processes as reversible because oftentimes the real process is often too hard to model, right? When we start to talk about internal combustion engines, there's a whole lot of assumptions that we're going to make, right? And like I said, every time we make an assumption, we're stepping away from reality towards sort of the cartoon of that reality. But that doesn't mean it's not useful, right? And oftentimes, the good thing about this is we can get some kind of an analytical equation, right? So just a problem you can solve with pen and paper, and you can see something like, what's the impact of changing the compression ratio on an internal combustion engine, right? And you can see what the cost and the benefit of those are from looking at a very idealized version of the system. Now, when you do this, it means that your numbers that you get aren't really correct, right? It's not going to be the exact right amount of horsepower that you're predicting in your model, but your direction is going to be correct, right? So if you make a change, you'll know, will that make the engine, produce more power, or will it maybe make it more efficient, right? Well, often as engineers, we always have trade-offs, right? And one of the trade-offs that we often get is power for efficiency, right? Although I don't know if anybody watches Top Gear, but in one of the old ones, they had a Bugatti, which is like 1,000 horsepower car, and a Prius, and they were racing them on a track. And if you push the speed up high enough, then the Bugatti was actually more fuel efficient than the Prius, right? Now that's obviously not going to be like me driving down, to get to work and back, right? But that's also an important sort of lesson for an engineer is, there's a correct tool for every application, right? So you got to think about where your operating parameters are, right? And that might help you pick the right tool, right? So if we know something about the ideal process, that can help us sort of compare against the real process, right? So I said, we might want to look for low-hanging fruit. So if we compare how we're actually doing to what this ideal process is, maybe the one that's furthest away from the ideal process, maybe that's going to be the one that's easiest to improve, right? Where we can get, good benefits for low cost, right? And that's nice, from an engineering standpoint, but also from an economic standpoint. So one of our jobs, I think, as engineers, is to think about societal benefit of things, and then kind of translate that into the language of dollars and cents for the business people who might be running a company or something. Right? So we're going to take a look at ideal processes versus real processes, right? So a reversible, right? So that's a synonym, right? If it's a reversible process, that means it's ideal, right? If it's an irreversible process, that means it's real, right? Or not ideal, right? So a reversible process has no irreversibilities, right? So it's like you're saying, I'm just going to assume that friction doesn't exist, right? That's what we did in high school physics, right? And we still learned a lot from doing that, right? So that can be useful, right? So in this ideal process, this thing we're going to call the generation of entropy, right? Remember, the second law told us entropy is always increasing in the universe, right? Well, if it's an ideal process, the very best we can do is not generate entropy. We certainly cannot reduce entropy, right? But maybe the limit of what's possible is no entropy generation, right? So a reversible or ideal process has no entropy generation, and a real or irreversible process has positive energy generation, that the entropy is always generated if we look at the whole universe. Okay, so hopefully as a concept, maybe this is starting to make sense, but for me anyway, sometimes I got to get my hands dirty, right? I got to start doing the math in order to really understand how to do a problem, right? So like I said, the second law is different from conservation of mass and conservation of energy because entropy is not conserved. It's always increasing, right? So how do we know how much is created or generated, right? We can use the second law of thermodynamics for this, right? So first we're going to look at the elapsed time version of this equation, right? So we have this delta S, or the change in the entropy in my system, right? That was like delta E. Remember, delta E is equal to Q minus W, right? This is that sort of elapsed time version of this equation. So the change in the entropy in the system is equal to the heat transfer divided by the temperature. It's important to take the temperature of the surroundings and not the temperature inside the system. And we'll see that a little bit further on. Right now, we can still have mass coming in and out, right? Like Donald and Goofy in the beanstalk, right? So I take, the mass times the entropy of all the specific entropy of all the stuff that comes in minus the mass times the specific entropy of all the stuff that goes out. And then I have this term. This term is kind of the whole reason that I do a second law analysis, right? The sigma term. This is my entropy generation term in the control volume. That's what CV means here. So I know for a process to be real or possible, that entropy generation term has to be positive, right? So if we look at this, right, remember I told you that entropy has the units of kilojoules per degree Kelvin, right? Or maybe BTU per degree Rankine, right? So it's easy to see from my first term, right? This is heat transfer, right? Which is energy, temperature. Now, this is not a temperature difference, right? If it's not a temperature difference, that means you have to use Kelvin or Rankine, right? You can't, right? Because otherwise you get a totally different answer if you put in 0 degrees Celsius or 273 degrees Kelvin, right? So anytime you have a temperature that stands alone, that's not a temperature difference, you have to use absolute temperatures, right? We can check the units here. The mass in kilograms times kilojoules per kilogram Kelvin, and we'll get kilogram Kelvin. That's the same for the next term, which must mean that my entropy generation term is also in kilojoules per Kelvin, right? So I'll give you a second to write that down. So physically, what does this mean? We kind of walk through this, right? But delta S is going to be the change in the entropy in the control volume over time, right? This is Q over S. This is the entropy entering into our system by heat transfer, right? So this is the heat transfer. This is the same Q you're going to use in the first law, right? So the sign convention is still the same, right? But the temperature is going to be the temperature outside of your control volume, or I guess more technically on the boundary of your control volume, but outside is better than inside. Then you've got some entropy that comes in and goes out with the mass. And then finally, the whole reason we're doing this, right, is to find the amount of entropy that's generated from this process, right? We know that if this was an ideal process, this term would be 0. And if it's a real process, it's positive. We know for sure that if it's negative, it can't happen. Right, so that's the elapsed time version of this, right? We know that entropy is not conserved, right? That's what the second law tells us, right? And mathematically, it means this value has to be positive if it's something that's going to happen in real life, right? So, right, any process that would, so in order for a process to happen in real life, it has to satisfy conservation of mass, it has to satisfy conservation of energy, or the first law, and it has to satisfy the second law, right? So in order to satisfy the second law, this number, sigma, has to be positive, right? So if it does not satisfy conservation of mass, the first law, and the second law, then this process cannot happen right? It's a figment of somebody's imagination. It's a perpetual motion machine, right? Sometimes, I guess, so it's only a perpetual motion machine really if sigma is 0. If sigma is negative, it's kind of like a perpetually accelerating system, which would be awesome, but doesn't exist in real life, right? So for a process to occur, the first and the second law must be satisfied, and so must conservation of mass. So that's the elapsed time version, which we generally won't be using, right? Although we could, right? But just like for other open system equations, we will divide all these terms by delta t and take the limit as delta t goes to 0, and we'll get this equation, right? So this now, my delta s turns into ds by dt. My q turns to a q dot. My m turns to an m dot, right? In both cases. And my sigma becomes a sigma dot, right? So that's sort of, denoting that all of these terms are rate terms. And just like in all the other equations that we've been using, this term on the left, that's d something by dt, this is talking about how much of that thing is being stored or depleted inside of my system, right? Now that's, again, I think that's easiest to think about, like with my cup that's out in the rain, right? But, you can have entropy in a system, and that entropy in the system could be increasing or decreasing over time, right? But at steady state, we know this one is going to go to 0 because that, d something by dt at steady state means nothing is changing with time. That must mean that the entropy stored in the system is not changing with time. All right, so just verbally, right, this ds by dt, this is the rate of change in the entropy within the system, right? So the instantaneous rate at which entropy is being stored or depleted will often, almost always, be at steady state. So this one will usually go to 0. This is now not just the entropy that's coming in with heat transfer, this is the rate, right? Because we're looking now at an instant, right? Any particular instant, not some elapsed time, right? So this is the rate at which entropy is entering the control volume by heat transfer, the rate that entropy is coming in with the mass, the rate that entropy is going out with the mass, and the rate at which entropy is being produced, right? Now, the good news is, what do we know about entropy generation? Right? We know that the entropy in the universe is always being generated, right? So that means the slope, if I plotted entropy in the universe over time, the slope would always be positive. Always, 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 right? And this is kind of like the slope of that line. So for something to exist in real life, right, this sigma dot term, it has to be positive, right, for real processes, right? Now, there's the limit of what's possible, right? And that's the ideal case, the case with no irreversibilities when we're neglecting friction, right? That would mean sigma dot would be 0, right? So this is still actually not possible, but it's kind of the limit of what's possible. And then if we ever do an analysis, the reason that we're doing this is to figure, is this process possible? If sigma dot is negative, then we know the process cannot happen in real life, right? That's the equivalent of taking a matchstick, unstriking it, right, and getting a matchstick back, right? It doesn't happen, right? It can't happen. It's a perpetual motion machine, or actually, like I said, maybe even a perpetually accelerating system, which we know can't happen, right? So this is the kind of analysis that we will do when we talk about the second law, right? So when we try to say, so if I ask you, is this process possible? You can look at, is the information given, is mass being conserved, right? You can say, is energy being conserved in this system, right? Or you can maybe do an open first law analysis and say, is entropy being generated, right? So is this sigma dot term positive, right? Or is it negative, or is it 0? Right, so now let's try to think about this in terms of these open system components that we've been talking about in class, right? So if we look at the ideal turbine versus the real turbine, right? So now this is kind of nice because I've been holding out on you a little bit, right? We've been drawing these graphs, right, as temperature versus specific volume. It's always a little bit hard for me to do that, right? Because I know at this point in the class, and for the rest of the class, we start to move to temperature versus specific entropy graphs, right? Now they behave exactly the same, right? They work the same. But you know, when we drew PV diagrams, the cool thing about PV diagrams was, you know, oh, if I took the area under the curve, that tells me the work, right? So there's something physical that I can figure out just by looking at the graph. The TS diagram also has this sort of characteristic where I can just look at a process sometimes and tell something about it, right? Which I don't really get from TV, right? So now we're going to often plot these things, particularly for open systems, as TS diagrams, right? And I'll show you why, right? So when we talk about a turbine, right? So let's first look at an ideal turbine, right? So remember the assumptions we were making before when we were talking about turbines? We said there, oh, let's say that the turbines is at steady state. We turned the power plant on. It had to, you know, warm up for a little bit, but now it's just humming, right? So nothing's changing with time, right? Now, we also, right, one inlet, one outlet in this turbine, right? You can see there's an inlet here and an outlet there. So those summation signs, they go away, right? We know that the system is adiabatic, right? Or at least what we're saying is, remember in the first law, when we talk about turbines, oftentimes we'll say, oh, the work term or the power generation term is much bigger than the heat transfer term. So let's just throw that heat transfer term out. We'll assume that it's small enough that it doesn't really matter, right? Now, if I also say that this turbine is ideal, right? I remember an ideal system means that the entropy generation rate is 0. That's the best I can ever do. I can't actually do that well, but that's the limit that I could maybe approach, right? And if I did that, then I would get this equation, right? Because there's only one mass flow rate, right? Remember from the first law, or from conservation of mass, we would see that the inlet mass flow rate must be the same as the outlet mass flow rate if the system is at steady state. So that means that 0 is equal to m dot times specific entropy in minus specific entropy out. Right? Now, if I divide both sides by the mass flow rate, then what I'll get, right? Because, you know, this system's only interesting if there's a mass flow rate going through my turbine, right? So if mass flow rate is not 0, right, then delta S must be 0. So S in must be equal to S out. Now, for a real turbine, it's a little bit different, almost the same, right? So ds by dt, right? We make the same assumptions, but now because we left this term to survive, we know that this entropy generation rate must be positive. So now, right, which is really the same equation from before, but before we had sigma dot be equal to 0. So here we know that sigma dot is equal to m dot times S out minus S in. Mass flow rate has to be positive. I know that the entropy in the universe is always increasing, right? So sigma dot must be positive for this process to happen, for it to be a real turbine. And that means that S out has to be bigger than S in a turbine, right? If I make all these assumptions. So that means that the entropy is increasing across the turbine, which kind of makes sense, right? Because the entropy generation is increasing in the universe, right? And we've crossed out all the other terms, right? So we got rid of this heat transfer term. Heat transfer term is the one that's the most difficult to deal with. And we'll start to talk about that next class, right? So here, I know that S, specific entropy at the outlet of the turbine, must be bigger than the specific entropy at the inlet of the turbine if I've made all these assumptions, right? So now, if I'm drawing this on a TS diagram, what this means is that my ideal turbine, right, has S out the same as S in, right? So we have this vertical line down. Now, this ideal turbine, we're going to call isentropic. Isentropic, that means the entropy across the turbine does not change, right? So we label this state, not just this state 2, it's like a special version of state 2, the ideal outlet, right? What would happen if the turbine was ideal? If it was isentropic, we call this 2S. So we put an S beside it to remind ourselves that this is the isentropic outlet. right? But just by looking at the graph, I can tell that if I know this is a turbine and I've made all those other assumptions, this vertical line is ideal because it's a vertical line. The real outlet of the turbine has to be to the right of the ideal outlet because I know that the entropy has to be bigger at the outlet. The specific entropy is bigger at the outlet than at the inlet, right? That's what the second law told me if that sigma dot term is positive and we've made all those other assumptions. So here I'm going to draw it just on that saturated vapor line, right? So the real process scoots over to the right. So now this line is going down and to the right because the entropy has to be increasing. Right? Now, for the ideal pump, then it looks like this, right? So it's very similar, right? Remember we said before, pumps and turbines, we make the same assumptions, right? So for the ideal pump, we're going to say that it's at steady state, that it's one inlet and one outlet, right? Remember we said that ideal pumps are adiabatic, right? But even real pumps, we're generally going to assume that the heat transfer term is much less than the power term, right? And if it's ideal, sigma dot is also zero, just like the turbine, right? So here, zero, which is really sigma dot, but we're saying that the ideal process, sigma dot goes to zero, right? That's going to be m dot times S in minus S out, just like it was with the turbine. So we know for this pump, we're going to have a vertical line, right? Because S in is equal to S out, right? This is also an isentropic process because I've assumed that it's at steady state, that it's adiabatic, and that it's ideal with one inlet and one outlet, right? So that means that ideal must also be isentropic. The real pump, just like the real turbine, we're going to make all of those same assumptions, except we'll relax the assumption about it being ideal, right? So if it's a real pump, sigma dot has to be positive, which means that the entropy generation rate, sigma dot, sticks around. And because that's positive, just like in the turbine, S at the outlet is bigger than S at the inlet. Right? So if we go back to our TS diagram, right, we go inlet at the pump. If you're ever designing a pump, you want to make sure that it's only liquid that goes into your pump. You don't want to go into your pump under the vapor dome, because if you let vapor into a pump, your lifetime of your pump goes down, right? So it causes damage to the pump, right? So here we want the pump to be, it's at the saturated liquid line here, the ideal pump, right? We're increasing pressure, right? So this is a low pressure down here. This dotted line is a higher pressure, right? The ideal pump has this vertical line between the inlet and the outlet, right? Now it's straight up. That's the ideal version of the pump. The real version of the pump, the outlet again is going to scoot to the right, right? Because the entropy increases. S2 is bigger than S1, right? And now we have a vertical line that's going up, but slanted to the right, right? Because the entropy generation rate is positive. So the entropy at the outlet is bigger than the entropy at the inlet. So when we talk about these isentropic processes, it only really makes sense because isentropic we kind of use as a synonym for ideal, because for these turbines and pumps, if it's isentropic, then it's also ideal, right? So that's only true because we've canceled out that heat transfer term, right? So life with the second law gets more difficult when we add in that heat transfer term. We're not going to talk about how that happens today, right? So next class, we will start to see what happens with heat transfer processes. And why, when I started to teach this class, right, I was talking to my brother, who's a biochemist. So he's a professor down in Binghamton. And I was telling him, I'm teaching thermo, and thermo's a real tough course, especially when we get to the second law, right? Conceptually, it's really hard. But the one thing that I know about the universe is that entropy is always increasing, right? And my brother looked at me and he said, but that's not true, because they took a class called physical chemistry, which is basically their version of thermodynamics. And he said, because if I run a condensation reaction, right, if I condense some water, the entropy decreases of the water. And what I told my brother was, Jeff, that's his name, you have to look at the whole universe. It's the entropy of the universe that's always increasing. And we'll see how that works next class when we start to talk about heat transfer rates, right? Because in that condensation reaction, there's heat transfer happening, right? When you're condensing something, it means that you're losing heat, so you can't get rid of that Q dot term. So we'll start to talk about that next class. Just a reminder, if you have questions about either the homework or the exam problems, I'm happy to talk about them today at 2 o'clock in office hours. I'll stick around for a couple minutes if anybody has questions about the material. Thanks, everyone.
Thank you.
Thank you.
Thank you. Thank you. Have a good weekend.
You too.